Hi there, and welcome to this lecture that's going to give you an introduction to the simple regression model. This is going to be the first of a series of lectures that's going to cover the basics of this model and why this is important to use. These are the three themes that we're going to be covering during this lecture. First of all, we're going to be defining the model, explaining what exactly it does and why it is important to study this model. Then we're going to derive the OLS, which means ordinary least squares estimate, which is how you estimate the parameters that are part of this model and why this model is so powerful. And then we're going to explain some of the properties and assumptions, because under a certain set of assumptions, this model is very powerful, and we're going to explain those assumptions to you and why they sometimes do not hold. So first, to give you a bit of a motivation behind the use of this model and why it's so important to study this. Many questions within econometrics or economics as well deal with the relationship between two quantities that we can possibly measure. For example, how do demographical factors affect unemployment, or how does the interest rate that the central bank set influence stock prices? These are all things we can measure and that we know are somehow related, and that we're interested in finding out how exactly those relationship works. Sometimes we have some intuition as to whether things influence each other positively or negatively or not at all. But it's difficult to attach a number to this and to say exactly, for example, being a male and a female or be living in a certain neighborhood affects the possibility of being unemployed by a certain number. And that's what a regression analysis does. It gives you a relationship between two variables and it quantifies this. It gives you a factor with which one variable influences another one. We can use this to model relationships to predict them in the future, or to better understand these relationships and to test whether the relationships we find are really statistically significant or they might just be due to random chance. So we've established that regression examines the relationship between two things that we're interested in, two things that we can measure, some variables. And in this case, we're going to be talking about one of them being the dependent variable, the thing that we're trying to explain, and the other one being the explanatory variable, which is what we use to explain the thing we're interested in. In one of the examples I mentioned earlier, the dependent variable would be stock prices, and an explanatory variable is the thing that we use to explain the stock prices. For example, the interest rate that the central bank sets, in the example I mentioned before. We're going to assume a linear relationship between these two things. So if the explanatory variable increases by some quantity, the dependent variable increases by some other quantity. These don't have to be the same, but there's one linear factor with which the explanatory variable influences the dependent variable. We can write this in a formula form as we see down below, where we use y to indicate the dependent variable, which explains of some constant factor alpha, with added on some part that's explained by the explanatory variable x multiplied by some factor beta. And in the end, we have what's called an error term. The error term is everything that falls out of this equation that we really cannot measure. We're going to assume that by just using the constant alpha and the explanatory variable that we have, we're not going to be able to explain y perfectly because of random noise or other stuff that we haven't included. All of this is captured by this epsilon. So you see that the explanatory variable x is multiplied by some factor b. This factor b explains to us the influence that x has on y, if any. B can be 0, in which case there's no influence there, and x doesn't affect y at all. But usually, if we have some intuition why x would influence y, we will see that the numbers are going to confirm this, and that b will have some influence on y, either positive or negative. So regression models are going to help us to quantify some linear relationship between what we call the explanatory and the dependent variable. We're going to assume that some relationship is there, and we're going to help the model find us exactly how strong this relationship is, or show us that in fact we were wrong and it was never there in the first place. So first of all, before running the linear regression model, we're interested in seeing if the data gives us some intuition if there's a relationship there to be examined. There's some quick and informal checks that we can do to see if the data gives us a reason to be interested in this effect and to estimate it using a regression model. First of all, we can make a scatter plot between the variables. We're going to show this later on in the presentation, but we're just going to plot the explanatory variable and the dependent variable in the same graph. We're going to see if just eyeballing there seems to be some relationship there. Another thing we can do is check the correlation between the two variables. The correlation roughly explains by what number one variable increases if the other one does as well, or decreases if correlation is lower than 0. Using these two checks, we can quickly see if some linear relationship seems to be there and use this as a basis for our regression analysis. As you've seen in previous slides, we're going to be using some notation where letters are going to be representing numerical quantities. The first example we have seen is the y and the x, where y represents the dependent variable and x is going to be the explanatory variable. The dependent variable, again, is the thing that we're going to explain, and the explanatory variable is the thing we're going to be using to explain this dependent variable. This is not going to change throughout these slides. The alpha and the beta are the factors that make up the regression equation. So alpha is going to be the intercept and beta is going to be the factor by which x influences y. Note that alpha and beta are the true population parameters that we assume to be there. We can never know this because we can never see the data generating process, but we can estimate them. When we refer to the factor that we estimate, we're going to be calling them A and B. Finally, the model is made up of an error term epsilon that, as we discussed earlier, is going to be including mainly noise or in some cases other variables that we have forgotten to include. We are not going to be estimating this epsilon as we're going to assume that it's beyond the scope of this model. So in the light of all the notation we've explained, let's go over the regression equation one more time. We can see the y, the thing that we're trying to explain, which we're going to set equal to some formula which is made up of alpha, some parameter which gives the constant in the population. Added on, we have x times beta, which is the effect of the explanatory variable x, and we have epsilon, which is some unknown part, some random noise that we cannot know, but we have to assume it's going to be there because we're never going to be able to explain y perfectly using only alpha and the explanatory variable x. The thing that regression analysis does is estimate these parameters. The alpha and the beta that we assume to be there, there are some true value that these parameters have in the population, but that we cannot see. So using what's called a sample, so the data that's available to us, we're going to estimate alpha and beta in the way that best explain the data that we see. So the data that we see only has the values of y and x, so the variable that we're trying to explain and the variable that we're going to be using to explain this y. And given this data, we're going to be estimating alpha and beta in such a way that the data that we have best align with the equation that you see here in the slide. So what regression analysis is going to do is it's going to give us a way to estimate these parameters alpha and beta in such a way that they, as much as possible, fit the data that we have available to us. This is a concept that requires some more examination, because what exactly do we mean when we say that some parameters is the best fit for the data? What are we trying to do when we fit a parameter? This is the first question that we need to answer. We need to find a way to estimate how well some estimate B that we have for the population parameter beta fits the data, how good it is. So a good idea is to look at the data first. In this slide, you see an example of two variables that could be modeled using a regression model. The first one being quarterly change in GDP and the second one being quarterly change in unemployment rate. When we just look at the point clouds, at the blue points that we have available to us, which are measurements, we see that there seems to be some negative relationship there. The higher the quarterly change in GDP, in general, the lower the quarterly change in unemployment rate. So we want a regression model to confirm this, to show us some negative relationship. And as we see, the black line, which is the best line that we can draw through the point clouds, indeed has a negative slope, a downward facing slope. The act of finding these two parameters, the alpha and beta, that best fits the data, is the same as the act of drawing a line through this point cloud. The alpha and the beta give respectively the intercept, so the point where the line starts, and the slope of that line. So the parameter beta is the same as the slope of the line that we draw through the points cloud. So saying that we want alpha and beta to fit the data as well as possible is the same as drawing this line through the point cloud in such a way that it best fits the point that we see in the graph. So the task in front of us is to try and find a way to formalize how good a parameter set works. Ideally, we would want the parameters to fit the data perfectly, so for there to be no error, but unfortunately in any real-life application this is not feasible. So what we're going to be doing is not look for the perfect model, but we're going to be looking for the model that's the least wrong, so where the error is the smallest. And we're going to be doing this using the idea of residuals. A residual tells us how far off the model is. So using all the information that's captured by the model, how much of a difference there still is to the data that we actually see. And this data again comes from our sample. As unfortunately we cannot never have all the data available to us that there is or that there ever has been, we're going to be using only the data that we can feasibly measure. This is what we call the sample, which consists of values for the variables y and x. The residual that we're going to be using gives for any point the difference between the value that we see for y, so for the dependent variable, and the value that we estimate using a regression model. The difference between these things is all the information that's unfortunately not captured by the model. This is what we call the error. We want this error to be as small as possible, because that would mean that we have as much of the information as possible captured by the model. In mathematical terms, what we're going to be minimizing is the loss function, which is given below. It's the sum of y minus x times beta over all the observations I. This is what we see here. We're going to square the values to make sure that positive and negative differences don't cancel each other out, and because it has some desirable mathematical properties later on. But the important thing to remember is that for each point I, we're going to look at the measured dependent variable, which is yi, and the estimated dependent variable, which is the value for x times this b, which is the estimation we have for beta. We're going to be squaring this, and we're going to add up for all the observations that we have available to us. This is the total loss function, or the total squared error of the model. This is the thing that we want to be as small as possible. So we want the loss function that we saw before to be as small as possible, or to be minimized with respect to some estimator beta. So we're going to be setting the variable b, or beta, in such a way that this loss function is as small as it possibly can be. If we want to minimize a function, and we're going to be choosing a variable in such a way that it minimizes this function, what we do is we take first derivative and we set them equal to 0, as you've probably seen in earlier courses. In this case, the exact algebra doesn't matter so much, so we're not going to be showing you this first derivative, and we're not going to be showing you how to set it equal to 0. But what comes out of it is what's called the OLS, or the ordinary least squared estimator, or for beta, which is given by this formula right here. It's the sum of x, the explanatory variable, times y, divided by the sum of the explanatory variable x times the explanatory variable x. This formula uses only the data x and y. So only having the data in the sample available to us, the x and the y's, will already give us an estimate of what this factor beta looks like, or what the best estimator is of beta, using only the data in the sample. This is the OLS estimator beta. This can be interpreted as the increase of y as the result of a 1 unit increase in x. So if x increases by 1, how much do we estimate y to be increasing? Note that this factor beta also can be negative, which means that if we increase x, y will decrease. But again, it will be given by the same formula. So what we've been doing so far is we've assumed that there's some factor beta, which is the true number within the population. So this relationship exists, and there's some number that describes this relationship, and we just need to find it, or find an approximation that's as good as possible using the data we have available to us. And this is what the regression model does. It gives us an estimate for this factor beta, and this estimate is given by the formula we saw on the previous slide. Now, we've alluded a few times to why this regression model is so special, why it's so widely used. And Now in this slide, you're going to be seeing why. Under a certain set of conditions or assumptions that we will be explaining later, the OLS estimator or the ordinary least squares estimator is what's called the BLUE estimator. BLUE is an abbreviation. It means best linear unbiased estimator. This basically means that if these assumptions are satisfied, the regression estimate has some properties that are not matched by any other estimator that can be found. And specifically, it alludes to two qualities of the estimator that we're going to be examining here. First of all, it says the best linear unbiased estimator. So the estimator is the estimate B is an unbiased estimate for the population factor beta that we're trying to find, which means that the expected value of the estimator that we have is the true value of the parameter. There might be some noise, but the expected value is going to be 100% correct. Next, it's an efficient estimator. Efficiency relates to the concept of variance. As we said, the expected value of the estimator is the true parameter value, which is what we want to find, but it doesn't necessarily guarantee that it's always going to be the same. The model doesn't guarantee that the estimate B that we have is going to be exactly the same as the population factor beta. It's only going to show you that the expected value is the same. But within the estimators that we can find where the expected value is the same, the OLS estimator has the lowest variance. This means that the expected value is the same and that there's no other estimator that's as sure about the estimate. So there's some others where the expected value might be the same as the population factor, but the variance is bigger. So the B that we find in practice, we cannot guarantee that it's as close to the population factor as we can for the OLS estimator. So in the previous slide, we've seen why regression models are so special and why they're so widely used. As alluded to, this quality, the blue quality, only holds when there's some assumptions that are true. These are the four assumptions that we're talking about, and we're going to be covering them in the next part, namely linearity, the error terms are uncorrelated, there's homoscedasticity, and the error terms are normally distributed, or normality. Next, we're going to be showing you every one of these four assumptions and why they're so important. First, we take the assumption of linearity. What this assumption says is that the regression formula y is alpha plus x times beta plus epsilon is actually the formula that describes the data generating process. So there's actually some linear relationship there. There are a lot of reasons why this assumption might not be true. Some examples that are given here is that there's multiple explanatory variables and some are left out, or that y is a binary variable. In this case, the formula y is alpha plus x times beta plus epsilon will probably give you some value for x that will lead for the variable y to be estimated to be bigger than 1 or smaller than 0. This is also some of the consequences when this assumption fails. When the range of y is limited and we estimate the regression model, it will sometimes give you predictions that are outside the scope of y. Moreover, parameter estimates are biased and predictions are generally poor, even when the scope of y is not limited. As you can see, linearity is an important assumption, so ideally people want to know beforehand if it seems to hold true or not, as we have just seen the problems that we can run into if this assumption does not hold. We're now going to be showing you a way to examine whether this assumption is true and some R code to do this for yourself with some real-world data. We've alluded earlier in these slides to something you can do to examine whether there's a linear relationship there that's to be estimated by a linear regression model. One thing we can do is we can make a scatter plot of the two variables. A scatter plot shows the two variables in the same graph, and it's going to be showing you if there's more or less a linear relationship, if the linear relationship has some other functional form, or if there's no relationship at all. This can be done by the first line of code that you see with some variables, variable 1 and variable 2. Another thing we can do is calculate the correlation coefficient. When the correlation coefficient is close to 0, it means that there's no relationship between the two variables, or at least no linear relationship. This can be calculated using the second line of code, using again the same variables, variable 1 and variable 2. Below we show two examples of some scatter plots between two variables. One of them shows a good linear relationship that can probably be estimated well by a linear regression model, and the other one shows a relationship that might not be so well suited to this type of model. Now take some time for yourself to decide which of these graphs you think shows a good linear relationship to be estimated by a linear regression model and which of the two doesn't. Here you see that the graph to the left shows a good linear relationship and the one to the right doesn't. You see that in the graph to the left, there's a good linear flow to the data. So if one variable increases by an amount, the other one seems to increase by a proportional amount, plus some noise that is there. In the second graph, we see that there's no line in the data. There seems to be no linear form. And also it seems that one of the two variables is capped at 100, which means that a linear relationship might estimate a value that's not realistic. Now on to the next assumption, which says that the error terms are uncorrelated. What this means is that if we have multiple data over time, there's no correlation between the error term of one period and the error term in the next time period. If this correlation is there, that means that the error terms of previous time periods contain information on the current observation that we're looking at. This means that there's information available to us that's not included in the model, and the model could be improved by including this information. It's important to note that this can only occur when we have more data over time of the same individual. This is a type of data called time series data, and this is the only type of data where autocorrelation, which is another word for correlated error terms, can occur. This can happen, for example, due to seasonal effects when we're measuring data on a monthly basis. The consequence is that OLS is no longer efficient if there's information that's not included in this model that could be included to make the model even more efficient. Luckily again, there's ways to find out if you think this assumption might be violated. In the case of this assumption, what we can do is we can plot the residuals for one individual and we can see if we think there's a pattern there that we can use to improve the model. The first thing we do is estimate the model. This is done by the first line of code. This gives us, among other things, the model residuals for one individual over time. We plot these residuals using the second line of code. And what we want to be seeing is that there's no information there, no pattern. So knowing all the residuals for this individual in previous time periods is not going to help us to estimate the next time period. Below you see two plots, or two ways these plots can look. One of them is the way you want it to be. So there seems to be no information in these residuals, and knowing the residuals up to a certain time point is not going to help you estimate the next time point. The other graph does show a relationship and gives you a reason to assume that there might be some correlation in the residuals over time. Now take a moment to decide for yourself which one of these graphs you think looks nice and gives us a way to assume that to think that this assumption is not violated, and which one that gives you cause for concern. So as you can see, the graph to the left is the one that looks the way we want it to, and the graph to the right gives us some cause for concern. The graph to the left is a very random point cloud. There's some positive observations, some negative ones, but there doesn't really seem to be a pattern there. And knowing all the observations up to a certain time point certainly doesn't make it easier to estimate what the next point is going to be. The one to the right shows some sort of sinoid. So there's some sort of cyclical behavior there, which means that knowing how the data looks up to a certain time point does help us to estimate the next residual, because it probably is going to be exhibiting more or less the same pattern. If we would see this type of graph, this gives us a reason to believe that there's some autocorrelation there that has to be included in the model to make it better. The next assumption that we're going to be dealing with is called homoscedasticity. Homoscedasticity deals specifically with the error term, epsilon, that we saw earlier in the regression equation. The error term epsilon is going to be 0 on average, but it's not always going to be 0, as it's impossible to fit all the data perfectly. Instead, it's going to follow a distribution with some variance. This variance is going to tell us more or less by how much we're going to be off when we're going to be predicting the dependent variable y. The assumption of homoscedasticity says that this variance is the same for every observation that we estimate. And therefore, every observation that we estimate contains the same amount of information. If some observations have a smaller variance, that would say that we can be more sure of the value that we see there in the data, as there's less noise that we cannot estimate using the model. As such, these observations should carry more weight when we estimate the model. Right now they don't. All observations have the same weight. We do this because we assume that the variance is the same. But when it's not, this can mean that there's information that's not included in the model. Heteroscedasticity, which is the opposite of homoscedasticity, so that the variance is not the same for every observation, can occur for a variety of reasons. For example, because there's more than one explanatory variable and some are omitted from the model, or because of outliers. Outliers are very extreme values that can be due to a number of reasons that are beyond the scope of this presentation. But for now, it's important to remember that when there's some very extreme values, this can lead to heteroscedasticity. The consequences are that when the error terms are no longer homoscedastic, this means that there's information there that's not included in the model. The estimates are still unbiased, so on average they're still going to be equal to the population values, but they are no longer efficient, which means that we can no longer say that their variance is lower than other estimates. Luckily, also for the homoscedasticity assumption, there's ways to find out if it seems to be violated or not. In this case, what we're going to be doing is we're going to be plotting the fitted value against the residuals. We do this by first estimating the model and then using the plot model line, which is going to give you some plots that can be used to check model assumptions. In this case, what we want to be seeing is that regardless of the size of the fitted value, so the estimated value of y, the variance of the residuals will stay the same. So they're going to be off by more or less the same size. In one of these graphs, that's the case. So in that case, regardless of the size of the fitted value, the variance of the residuals seems to stay more or less the same. In another one of these graphs, as the fitted value increases, the variance of the residuals also increases, which is undesirable. Take some time for yourself to find out which of these graphs seems to be correct and show the behavior that we're looking for, and which one of these gives you cause for concern. As you see here, the graph to the left shows the behavior that we're looking for, whereas the one to the right gives us cause for concern. In the graph to the left, you see that the points seem more or less randomly distributed around 0, between 2 and -2. This range does not change if you go to the left or the right, so if the size of the fitted value changes. The one to the right, however, shows that to the left of the graph, so when the fitted value is small, the variance of the residual is also very small and they seem densely distributed around 0. But as the size of the fitted value increases, so if we go further to the right of the graph, the variance of the residual also seems to increase. This implies that we're more sure about some observations than we are about others, and this is information that should be included in the model. The final assumption that we're going to be dealing with is called normality. Normality again refers to the residual epsilon from the regression equation that we saw before. In the previous assumption, we explained why we have to say that this residual follows some distribution. And in the previous assumption, we dealt specifically with the variance of this distribution. Now, in the final assumption, we're going to assume that it follows specifically a normal distribution. There are a lot of reasons why this might not be true, why in fact the data will not follow a normal distribution, such as the presence of outliers or the dependent variable not being continuous. If this variable is not true, the estimates of the model are still unbiased, consistent, and efficient, so all the desirable blue properties are still there. What changes is we can no longer make confidence intervals or perform hypothesis tests for these estimates, as we do not know what distribution to follow. Again, luckily, there's ways to find out if this assumption is violated or not. In this case, what we do is we plot the model residuals against the percentiles of the normal distribution. So on one axis, we have the model residuals, and on the other axis, we have the quantities that we would be expecting to see from a normal distribution. We would want this to line up more or less perfectly. So we want there to be a straight line between the model residuals and what the data would look like from a normal distribution. One way to do this in R is to download the car package and use the line that we see below when model is already estimated as we did before. Below we see two graphs, or QQ plot as they are called, where on one axis we have some variable, in this case the model residuals, and on the other axis we have the quantities as they would be expected to be in the normal distribution. Again, one of these two graphs looks the way we want it to be, so the data looks normally distributed, and the other one gives us some cause for concern. Again, take a moment for yourself to think which one of these graphs looks good to you and which one will lead you to think that this assumption might be violated. So again, it's the one to the left that looks good, and the one to the right that gives us some cause for concern. In the one to the left, you see that there's more or less a straight line through the data. So the data as we see them, the model residuals, are more or less as we would be expected to see them in a normal distribution, with some error that might be there due to random chance. The blue bar that you see gives us a confidence interval, or a range within which we would expect the data to fall, even if it might not follow the line perfectly. In the graph to the left, you see all the data falling within this range, so not giving us cause for concern. Whereas in the one to the right, in the beginning, you see some points that are definitely out of this range. And also, eyeballing there does not seem to be a straight line there, which suggests that at least in the tails of the data, as it's called, it does not follow a normal distribution.